Good morning, everyone. Today, we will present our work on validating an ultra-low power plant impedance sensor implemented in a 90 nanometer CMOS technology. The goal of this work is to determine whether a sub-10 microjoule sensing architecture remains accurate, reliable under real-world silicon variations. To achieve this, we perform a complete process temperature voltage analysis or PVT analysis using Cadence Virtuoso on GPDK90 technology library. In total, we executed 3,600 transient simulations covering multiple process corners, supply voltages, temperatures, and plant stem impedance.
Our presentation will first explain the sensing principle, then discuss why the circuit becomes vulnerable under process variations, and finally show how compensation techniques restore robustness. The sensing
The same.
principle is
Mhm.
based on Schmitt-trigger relaxation oscillator. The plant stem impedance acts as a resistive element in the RC network. As the stem impedance increases, the charging and discharging of the capacitor becomes slower, so the oscillation frequency decreases. Therefore, frequency is inversely proportional to stem impedance.
This is important because the sensor output is already in the form of digital pulses instead of using a complex ADC or signal processing chain. The microcontroller only needs to count pulses that significantly reduces circuit complexity and power consumption. The main reason we selected this topology is its extremely low energy requirement. Compared with conventional impedance measurement systems such as AD5933, which requires ADCs and digital signal processing, our oscillator methods consumes more than an order of magnitude less energy. It also produces a direct pulse output rather than an analog voltage.
This makes the design specially suitable for agricultural IoT applications where sensors may need to operate autonomously from harvested energy or in remote fields with no battery replacement. However, the circuit is not automatically robust. The oscillator frequency depends on the upper and lower switching thresholds of the Schmitt-trigger. Under the manufacturing variations or temperature changes, transistor threshold voltages shift. This changes the hysteresis window. If the hysteresis window becomes wider, the capacitor takes longer to charge and discharge, which lowers the oscillation frequency.
The critical issue is that the circuit may then interpret the same plant impedance as a completely different value. In other words, the sensor produces a false measurement even though the plant itself has not changed. To understand this quantitatively, we derived the analytical sensitivity of the oscillator. Ideally, the frequency should have a perfect inverse relationship with resistance, giving a normalized sensitivity of -1. Our derivation confirmed that this condition is preserved.
But we also found that the Schmitt-trigger threshold voltages have a very high parasitic sensitivity, greater than 0.79. That means even a small shift in transistor thresholds due to process or temperature causes a disproportionately large error in frequency. To verify the design thoroughly, we built a complete PVT test matrix. We simulated 5 process corners TT, SS, FF, SF, and FS. We swept temperatures from -40 degrees Celsius to 125 degrees Celsius and supply voltage from 1.62 to 1.98 volts.
In addition, the plant stem resistance was varied from 10 kilo ohms to 1000 kilo ohms. Combining all these parameters produced a total of 3600 transient simulations, giving us full coverage of both nominal and worst case conditions. This slide shows the frequency versus time resistance for all process corners. A key observation is that all curves remain linear and parallel. This means the fundamental sensing relationship is preserved. The slope does not change significantly, so the circuit still tracks resistance correctly.
However, the entire curve shifts vertically depending on the process corner. Fast process corners produce higher frequencies, while slow process corners produce lower frequencies. These offsets can exceed the acceptable low tolerance band of minus or plus 15%. At room temperature and nominal supply, the worst case frequency deviation reaches approximately plus 16%. So process variation alone is enough to push the measurement outside the allowable range.
On the other hand, power consumption remains remarkably stable. Even across all process corners, the circuit stays below 30 microwatt budget. Therefore, accuracy is the main problem, not energy consumption. As we next studied temperature effects, temperature increases, the switching thresholds of the transistor also increase. This widens the hysteresis window and reduces oscillation frequency. The result is nearly linear thermal drift of about minus 0.12 percentage per degree Celsius.
Across the entire temperature range from minus 40 to 125 degrees Celsius, the total drift reaches nearly 20%, which is even larger than the process induced error. An important insight from our study is that the process variation and temperature variation do not behave in the same way. Process variation creates a fixed offset. Once a chip is fabricated, that error remains approximately constant. Temperature variation, in contrast, creates a dynamic drift that changes continuously during operation.
Because the two mechanisms are physically different, they cannot corrected using a single compensation technique. We also investigated supply voltage sensitivity and random mismatch. The oscillator proved relatively immune to supply changes because the RC timing dominates the behavior. The worst case frequency shift due to supply variation stayed within about 6.8 percentage.
Monte Carlo analysis further showed that local transistor mismatch remains tightly bounded, so it is not the dominant source of error. When we combine all error sources, we obtain the worst case measurement budget. Temperature drift contributes nearly 20%, process variation contributes around 16%, and supply fluctuation adds another 6 to 7%.
The total error is therefore much larger than allowable 15% tolerance window. Without compensation, the raw sensor output will not be reliable enough for field deployment. To solve this problem, we propose a hierarchical compensational strategy. First, process-induced offset is removed using one-time post-fabrication digital calibration. Second, temperature drift is corrected dynamically using an active thermal compensation circuit that adjusts the switching thresholds.
Finally, supply fluctuations are suppressed using a low dropout regulator and a stable band gap reference. Together, these techniques bring the error back inside the required tolerance window. In conclusion, our study demonstrates that the relaxation oscillators remains fundamentally linear and ultra-low power across all PVT conditions. The main challenge is not preserving the sensing mechanism, but controlling the offset and drift introduced by silicon non-IDMs.
With the proposed calibration and compensation methods, the design becomes silicon ready for in vivo plant telemetry and agricultural IoT applications. Thank you. We will be happy for seeing you again. Thanks a lot for seeing our research. Have a great day.